Okay, so our next talk is going to be FFT computation towards exascale. And this will be co-presented by Stan Tomov and Ayala. So Stan Tomov received his MS degree in data science from Sofia University, Bulgaria, and PhD in mathematics from Texas A&M. He's a research director in ICL and research assistant professor in EECS at UTK. His research interests are in parallel algorithms, numerical analysis, scientific computing. Currently, his work is concerned on the development of numerical linear algebra software, in particular Magma for emerging architectures for HPC and FT for FFT distributed computations. And our second speaker is Alan Ayala, who's in person, received his MS degree in applied mathematics from Ayala at Mary University and PhD from Sorbonne University and INRIA Paris. I probably mispronounced that. He's a research associate at ICL at the University of Tennessee, Knoxville. Dr. Ayala's research focuses on the development of FT library for FFT computations on upcoming exascale systems and FFT benchmarking software initiatives. So let's, welcome our speakers.
Thank you for the introduction. I think I'll try to share screen. So the title of the talk is Towards Exascale FFT Computation, a survey, benchmark, and MPI challenges. We are the main developers from the Innovative Computing Laboratory, and then we have outside collaborators from Oak Ridge. This is Miroslav Stoyanov, for example. This is the summary of the talks. I will start with the background. I hear feedback, I'm not sure. So with background, I will define what is the FFT and then briefly introduce the main techniques on distributed and multi-GPU FFTs, how we do it, and what is the functionality that we currently have and provide. And then Alan would concentrate on challenges and current performance and future optimization techniques that we are targeting. So FFT, this is an algorithm developed in 1965. This is the Cooley-Taki algorithm, and it's considered one of the top 10 algorithms of the 20th century. By definition, mathematically, this is what a multidimensional FFT is. So as you can see, you would have some input vector of size n, and the output would be also of size n vector multiplied by these different frequencies of sines and cosines. So technically, this is a matrix vector product. One can look at this as a matrix vector product that would be of order n square flops. This is the discrete Fourier transform. But the FFT actually can do this in order n log n times. So this makes it extremely fast, especially since you can solve actually PDEs with the FFT. So usually an FFT, even to assemble a dense matrix of order n square elements, you would need n square elements. And a solver, typically like a dense solver, would require at least n square flops, unless one goes to sparse and other methods. And FFT, actually, it is going to solve this even less than a matrix vector product. It will do it in order n log n time, almost as if to write the solution right away. And this has many important applications. These are some of the applications that are of interest currently in the Exascale computing project funded by DOE. So mostly these are particle simulation codes, molecular dynamics, as listed here. So you have cosmology, this is the HAC code, a lot of signal processing, molecular dynamics, and particle simulations. Also, outside the VCP, we have collaborated with deep learning framework tools that need these type of codes, also PD simulations. The building block for the library that we are developing is for a single node, and there are multiple libraries here as listed. So actually, we have discovered more than 20 libraries that compute FFTs. Many of these are highly popular, like FFTE, vendor libraries, FFTW. And we work with most of these developers, and the way our library is organized is actually to try to reuse some of these developments. So we will use single node developments and try to reuse efforts like this and use them as backends to our library, Hefty, to provide distributed functionalities for exascale systems. Also, we developed a benchmark to test all these libraries and to benchmark them. And that's one of the reports that we have written about this. If we benchmark current implementation on a single node, this is what you get. So we target different architectures. We want to have support for all GPUs from NVIDIA, AMD, and Intel. And that's one snapshot of current performance on some of those architectures. So this is in terms of gigaflops per second, double complex precision calculations. In terms of what is the algorithm, this is a schematic view how 3D FFT algorithm looks like. So you have a input processing grid and output processing grid that may look something like this, where we have marked where is MPI rank 1, for example. So on the first step, we will do computations where processor 1 would collect so-called pencils. These are the one-dimensional vectors in one of these dimensions. And then each processor would have a set of those 1D pencils, and then they would compute the local 1D FFTs or 2D FFTs, depending on how we do the splitting. After that, the data would be packed to be sent over MPI communications in another direction to do the FFTs in. So if this was X direction, then we would like to do it in the next direction, Y or Z, and this is what this loop is. And then we will do the MPI exchange to transfer this data. So after that, the corresponding MPI process would unpack and possibly put it again, the data in contiguous memory in pencils in the other direction so that they can compute the FFTs in that direction. And we have tried various combinations to do this with point-to-point communications, collectives. Also, one can pack those three procedures in a single all-to-all W. And we have explored different ways and have parameterized our code so that we can get the best parameters for different architectures. And that's a paper that describe all these advances. So moving to parallel FFTs, this is a set of libraries that again we have looked into, and we collaborate with many of these people. As I mentioned, we have a benchmark also, and this benchmark actually encourages or motivates many of these developers to work with us and try to introduce improvements in their own libraries. The ones that we have highlighted here are the ones that support GPUs. So at least for the Exascale project, we are interested in libraries that support GPUs. Currently, Hefty, this is the library that we develop, is the only one that actually supports all vendors from NVIDIA, AMD, and Intel GPUs. As I mentioned, Hefty is the library that we developed, stands for Highly Efficient FFT for Exascale. So it's part of the ECP project funded by DOE. And it is integrated in a number of ECP projects already. So, and it has a number of unique features that I would just mention very briefly, like batch FFT, convolution, sine, cosine transform, and mixed precision FFTs. To introduce the challenges that Alan is going to talk more about, here on the left, we have a profile of a typical FFT codes running on multi-core CPUs. So as you can see, half of the time is spent on computation and half on MPI. When we introduce GPUs, this part gets highly accelerated, 40 times in this case. So technically it becomes almost zero. So the rest is MPI. So almost everything now is in MPI communications, and this is what our interest is here to. And we have started collaborations and talking with Dr. Panda's group and tools also like Samir with Tao, how we can further accelerate this part that is mostly into MPI right now. So that's just to illustrate one of the applications. So many of the applications have their own built-in FFTs. So they have application-dependent optimizations, like in this case, LAMPS is using FFT MPI or Swift. But still with Hefty, we managed to accelerate this. So in this case, I'm showing 1.76 times acceleration. The other routines, it's batched. If we have multiple FFTs to do at once, we can do it. This is on Summit and Spock. We get about 2 times speed up when we do batching versus not batching. And then there are special operations like convolutions. We can accelerate these also significantly compared to some other libraries. As it is difficult to accelerate the MPI, we are also looking into ways to just reduce the communication, in particular with mixed precision and data compression. This is also of interest to the group here. And it's another area that we would like to collaborate. Basically, when we reduce the data traffic, this introduces significant similar performance improvement as illustrated on these graphs. Also, since computations do not matter so much, we always would do the computations in FP64 arithmetic, and that would give us, in terms of accuracy, about an order higher accuracy than if everything is done in the lower precision. And we have this paper actually also accepted to cluster. I remember Dr. Panda mentioned another paper from the MVP group accepted there. And with that, I'm turning it over to Alan. I think I have to stop share. Alan?
So thank you for the invitation again to present our library. And in general, we are going to talk about FTT and also our benchmarking initiative. As Stan was mentioning, the FFT, when you move everything to the GPUs, where you can move to the GPUs and use a distribution of MPI that's CUDA aware, for instance, or GPU aware in general, we can see some experiments on large-scale systems like Summit. Here we're showing an experiment using 6,000 B100 GPUs. The FFT, the parallel FFT scales linearly, as you can see here, for both single and double precision, the both type of algorithms that most libraries supports, pencils and slabs, until a breakdown point. So this depends on the MPI distribution that you're using. And you can see there at some point here, for instance, when we have a 128 or 256 nodes, this slab, the composition tends to break the linear scaling. So, and but in general, we can have a linear scaling up to a breakdown point. If you increase the problem size, and this happens because of latency issues, here the message size become very small, and latency is more impact has more impact on the runtime. Here, if you increase the problem size, here you can see on wiki scaling, we can also get linear scaling. This is on Fugaku nodes. We used up to 1 million, more than 1 million Fujitsu cores for this experiment. And you may think that only happens to FFT, but it's not the case. When we implemented our harness for benchmarking FFT libraries, we observed that for several libraries from the state of the art, here on the left, you have for CPU-based libraries. You can clearly see this breakdown point when scalability stops being linear. This happens with most libraries. FFT and 2D decompose tend to give the best performance, but at some point, both of them break down as well. And this for CPUs. On the right, you have for GPUs. There's also a breakdown scalability. Here we have FFT-E from Tsukuba University, ACC FFT and FFT both versions. They all have the same issue on scalability. This is related entirely to the MPI, what MPI is doing for these cases, either on binary communication or collective communication. So if we zoom up here, we take the 4 nodes case, and we make a zoom what's happening here, and we can use vampire trace, vampire visualization here, and you can see that pretty much everything is going to communication here, the all-to-all. As Stan was showing, it's over 95% going there. This is the output that FFT gives you, the grids, the intermediate grids for each of the 3 directions of the 3D FFTs. And this is what happens. So the scaling problem that we are seeing is entirely, you will see the same if you just benchmark an MPI all-to-all V code. And what happens if we move from collective to point-to-point? The same. So the point-to-point will also dominate here. This is non-blocking send and receive implementation of parallel FFTs. It's also dominating the total runtime with 16 GPUs. So at large scales, if we just run the MPI all-to-all and see what's going on, you can see here the variability. Here you can see the network impact. Here, when you have 6,000 GPUs, you are using 1,000 nodes of summits, which is 25% of the total capacity of Summit. You see a large variability. This is because when the messages are small, the network usage from other users highly impacts your runtime as well. So this could be interesting. That we had a talk yesterday with the DPUs. We are evaluating how can we take advantage of that to better manage this kind of problems. And you can see here our paper where we show many experiments using different MPI distributions, including MPI pitch, OpenMPI, and Spectrum MPI, to see how this behavior varies among them. So to accelerate the computation of FFT, what can we do? We can evaluate. At the beginning, we thought, well, you are using just a set of MPI processor grids, and you have shown results where the scalability stops being linear. And what happens if we change our grids? Our processor grids, we can define it manually. Here, for instance, I fix p = 5, and we will make a q vary. So this is the values that q will take. And you see that for some values of q of the processor grid, the scalability stops being linear. But for other, it continues being linear up to 6,000 GPUs. Excuse me, this is for CPU experiment. We use over 40,000 Power 9 cores. So you see that for some cases, you can present this experiment on scalability and say, well, this library P3D FFT, which is from the San Diego Supercomputer Center, it stops scaling at this point here at 64 nodes. But this is not the case, actually. If you change your processor grids, you can keep scalability being linear. So that we can do it manually, as you can see here. But we all can also do it with auto-tuning. We have been collaborating with Cheryl Lee's group from Lawrence Berkeley Lab. And we can do that automatically. Well, integrating Hefty with GPU, you can see here on this link the code. It's a Python code to use auto-tuning within Hefty, and this will give you the best setting for your processor grid. Another thing that's very important is deciding between slabs and the pencil decomposition. So this is the 1D or 2D decomposition, and this will define how many tensor transpositions you do. Here in this case, for a slab, you only have one step of tensor transposition, and here you have two. So we have developed a communication model, and it's architecture dependent. Actually, this is only for Summit, where you can input your MPI process and your FFT size. And in this phase diagram, you will get which algorithm will be the fastest for this situation. So using that, you can ensure pretty much always linear scaling. Here, you can choose a combination either of pencils or slabs, and either binary or collective communication. So this is manual tuning. Choosing between pencil and slab can mean around 30% of benefit. The impact of binary or collective is more important large scale. And at some point, we just are limited by the MPI collective communication and what we can get from MPI distributions like MPI pitch. So we have been trying to get these communication matrices and get precise information what the MPI is doing for our particular case. We have been using these profilers from NVIDIA, from AMD, and mainly this available on Summit, like Vampire is available. It's a vendor profiler, but it's available for users from Oak Ridge, and Scorpio. So, and there's also collaboration with Dr. Panda's group for OSU INAM. That's ongoing. It's ongoing collaboration. So, what these profilers have in common, they have in common that many challenges that you can see here. Some of them have very limited support for modern C++. What does it mean is that, for instance, Scorpio, Cube, or Escalasca, they don't trace very well C++14 or C++17 when you use lambdas, for instance. We have in Hefty implementation, we have many lambdas functions that are in charge, for instance, of the local 1D computations. And they are not showing the profile because they simply don't support lambdas. And what happens also with some other profilers is that they don't support all MPI distributions. They are sometimes targeting MPI pitch or OpenMPI and so on. And some of them don't support GPUs. And if they have support for GPUs, sometimes it's vendor specific, for instance, for NVIDIA GPUs only. And it's hard to perform user-specific requests. If we want something specific on the code to be profiled in a specific way, it's hard to develop a code to tell the program to do that. So And there is also something that we have not yet seen in any profiler, is they are not architecture aware. They don't show you what the network is doing, where the congestion is happening. And in general, developing a profiler from scratch, it takes a lot of effort. So we don't have any definitive answer for that. So what we did here is to develop something very simple, very unorthodox, I also will say. It's just a profiler specific for FFTs. It's just in prototype level as well. And Hefty already provides you a tracing tool when you compile with the tracing enabled. And here you can see some, this is unorthodox actually. It comes from an analogy, a simple analogy. When you use your network from a computer and you do an analogy to a vehicle network, so you can have this kind of analogy. Network traffic, it's analogous to a vehicular traffic. The memory unit here, for instance, can be a unit of a double, can be a vehicle, and practical bandwidth, the average velocity, and the peak bandwidth can be the road capacity. So what we simply do here is we took Hefty tracing, we created a Python program, we did the interface with Transcat, which is a model that is a software that allows you to model traffic in a micro and macro environment. And we can have a visualization tool that's available for Hefty. So it can give you the variation. You can have the architecture, exactly what's happening here for Summit. You have the 6 GPUs, you have the NIC, you have the power NICE. And it can also give you on time what's going on, the network trafficking at, this is just for one step of the transposition. It can give you how much data is going in each of the lanes connecting two building blocks. They are very easy. So the reason why we did it like that, we didn't want to create something from scratch. So we just took a visualization tool that can take our output from Hefty and show us something here, architecture aware. It's very unorthodox, as I was mentioning. And finally, our Hefty is funded by the Department of Energy, as Stan was mentioning. And these are our collaborators from NVIDIA, from UTK, and from Dr. Panda's group. We have been also working with the Xtune ECP project for tuning, Dr. Takahashi from Tsukuba, and Dimitri from the Supercomputer Center at San Diego. And that's it. Thank you.
Slide the speaker, please. Do we have any questions? Dongla, please go ahead.
Yes, absolutely. Is it showing?
Yeah, here. Yeah. So what's the difference between left and right?
Difference what between what?
What's the difference between the left figure and the right figure?
The left figure is for CPU-based libraries, using up to 32,000
Okay, on the right is
GPU-based libraries. So this libraries here, for instance, FFTW doesn't have GPU support. P3D FFT also doesn't have GPU support. So this is only CPU-based. This is GPU-based.
So, but looking at this, it looks like there's a lot of different application hierarchy. There's a different version of the, at least from the CPU part. So what's your overall feeling about the scalability of these different library implementations on the CPU based?
So each library has the different communication framework. The FFTE, for instance, uses non-blocking all-to-all.
Oh, FFE?
Yes.
Okay.
So all of them, the only difference is that you compute the packing and unpacking and the FFTs on GPUs instead of doing on the CPUs.
Then when you compare this, because they're using different type of collective, MPI collective.
They all have different types of MPI.
Now, what part is because they use the different MPI collectives, so you get the performance benefit? What is because
You get, yeah. This difference comes just from the MPI we're using mainly, because the kernels are very small on runtime, percentage of runtime.
so from here, it looks like ACC FFT is the best, or at least most of the time.
Yes. At least most of the time, ACC behaves like this. And ACC implementation is with all-to-all. So our all-to-all behaves worse than ACC FFT, but if we use our P2P non-blocking communication, we can get faster.
Okay, then if you look at that curve, for a smaller one, you have higher overhead, but you have a better scaling.
Yeah, that's correct.
Okay, what's the reason for that?
Well, that's a question for the MPI people, maybe.
Okay.
Why they scale differently. This is a spectrum MPI.
Okay, thank you.
Yeah, okay.
I have two questions from the chat. The first is, how does FTT plan which MPI communication approach to use out of the various available methods for the MPI transpose? This is from ePlob.
So for MPI, we have been experimenting with three mainly: MPI pitch, Open MPI, and Spectrum MPI. And we actually, you can go to our benchmark here. This benchmark performance experiments a recent report that we released comparing different MPI distributions. And we have an experiment showing how MPI pitch performs better for when the problem size becomes very small, meaning for this using like 6,000 GPUs. There you can have a better performance using MPI pitch. When you have a small number of nodes, Spectrum MPI and MPI pitch behave pretty much the same. Open MPI and Summit behaves very badly. I don't know why. But so far, when we have a small problem sizes, we go to MPI pitch. And this is mostly for application people in machine learning. They have a small size problem. And we currently are just selecting this manually. The choice of the MPI is manually for now. It's another question.
Okay, and then the second question is, where can I find your slab versus pencil selection tuning related benchmark data publicly?
Okay, that can be found in this paper. And we have the selection of pencil and slab decomposition. As I was saying, it can be done with auto-tuning or using these phase diagrams that I based on communication model. It depends on the latency and bandwidth of the underlying architecture. You can find it in that paper.
Okay, so let's thank the speaker again, please.
Thank you.
So our next talk is going to be